and welcome to Module 3 of INST728E on social media and crisis informatics. And in this video, we'll be talking about using JSON to parse social media data. So first off, when we can look at social media data that's stored on a file on our computer or stored in some archive somewhere, odds are it's probably going to be stored in JSON, which looks something like this, where you have a bunch of these text fields with some value associated with them. And you can have arbitrarily nested fields like coordinates here with a type and a nested coordinate field for the entities field with nested symbols and user mention field, etc. So what is JSON? So on the right-hand side of the screen, we have an example tweet from Ferguson, Missouri, with a bunch of metadata around the tweet. While you may think of a tweet as being limited to 140 characters, in reality, a tweet has a lot of metadata associated with it in terms of not just the text of the tweet itself, but the unique identifier for that tweet, how many times it's been favorited or retweeted, where it was posted from, who posted it, what that profile looks like for that poster, how many hashtags it has or screen names it mentions. All this different content is stored in this JSON format with all this metadata. So JSON itself, which stands for the JavaScript Object Notation, is similar to XML, or the Extensible Markup Language, which was very popular in the 90s and early 2000s, but was often frustrating to developers because of its draconian structure requirements. JSON, however, is much less structured than XML and really just has a key value kind of field. It is more flexible than CSV files because CSV files have only one layer of nesting, so you can't have a field within a field in CSV. It doesn't make sense for a column of your spreadsheet in Excel to include more data than just that column. Whereas in JSON, as I mentioned, we can have a user mentions field that contains a list of all the user mentions. How would you do that in CSV besides having an extra column for every possible or for every number of user mentions that you may have? So JSON, as I mentioned, it's built around key value pairs, very similar to Python's dictionary or JavaScript's dictionary as well. So why do we care about this as a format? Well, primarily because it's used as probably the most common data exchange and storage format for social media data. So if you go look at some of the large archives of Twitter data, it's all likely to be in JSON. And most API responses are provided to you in a JSON format now, and we'll see that in some of the next modules. So fortunately, since JSON is so common, parsing it is relatively straightforward and well supported by Python. So Python has a package called JSON that has all kinds of native support for us. Basically, you call json.load or json.loadf. Here, this example is json.loadf, which means load from a string. And this string can be a set of keys and values. And this json.loadf function returns a Python dictionary. And then this is the library that we'll use to parse Twitter data and some Reddit data and Facebook data, and we'll see in the next few modules. All right, so before I go into the notebook for this module, I want to talk briefly about the Module 3 homework. It's very similar to the Module 2 homework, where you looked at Reddit post titles from a CSV file, but instead of using Reddit posts, we'll look at tweets, and I'll have you parse out tweet text to find the most common hashtag or most common tokens, and parse out entities within tweets to find the most common hashtags, and the user profile fields within tweets to find the most common users as well. And then for additional resources, if you want to read up on some additional information about Python and JSON, there's a nice YouTube video available here. All right, so now we flip over to the Module 3. We'll start that up and look at a couple examples of JSON data and parsing JSON data. So first, we have a little description. I encourage you to read this. It talks about RESTful APIs and Python's JSON support. And then we will import a couple of packages. So these first two, gzip and OS packages for Python, we'll see those in a few minutes. They're necessary for decompressing compressed files, which I'll talk about, and this OS package is useful for finding paths to files. But then we have the JSON package, which has all of Python's native JSON operations. And then we have an LTK, which we'll use for frequency distributions in an example at the bottom of this notebook. So we'll go ahead and run those. And then we'll look at a simple JSON example. So first, as I mentioned, JSON is built around keys and values. So key value stores are generally use JSON. For example, here we have a simple JSON string that has a key called car make and a value called BMW. First off, we have this JSON string. Note that car make and BMW are surrounded in quotes, and we can then call the JSON.loadS function on this string to create a dictionary from this string. We can print out the resulting dictionary, which would be no different than if we created a dictionary directly in Python. And then we can look at the value associated with the car make key in this dictionary. And this will give us back BMW. But if we try and look for the value associated with the key BMW in this dictionary, we'll get back an error because there is no key associated with BMW, only a value. So you go run this, and we see key error, exactly what we expected. There is no BMW key, but data stored in the key for car make gives us the value BMW, and we have this resulting car make BMW dictionary. And we can make more advanced JSON structures, so rather than just having one key value pair, we can have a series of key value pairs. So here's a JSON string for an object that describes a person with a name and an occupation and a goal. So we can load this into a dictionary like we saw before using loadS, and then we can print that out too. We can make this arbitrarily complex, so we can get an object, a person object, and we can encapsulate that or put that within an array of other people that we can construct within JSON itself. So this is a JSON string that has a people key and a value of an array. And in this array, we have one name, occupation, and goal person, and another name, occupation, and goal person. So we can run this, parse the JSON into a dictionary. We can print the resulting dictionary, and then we can iterate through the resulting dictionary or each value in the people array, just as we had if we had a list of arrays, or excuse me, a list of people that we had created as a list in Python directly. So here we have the full object, and then we have each person printed out as a Python dictionary. So we don't actually have to have the people descriptor, this people key, that surrounds this list. We can do this directly in JSON, so we can just have a list that has a couple of different people here. And the objects don't have to have the same fields. So if you notice here, this person whose name is Cody and occupation is student and goal is PhD. This person who's named Scott has an occupation and a goal, but also has an additional field for completed that is missing here. So we can go through and run this, and we get the same kind of thing. Everything works the same way, and when we go through the list, rather than looking at the value associated with people, as we did up here, we just look through the list that was within this JSON string, and we can print out each person, and we see here that this person's keys and values, or this person's keys, are different than this person's keys. And we can get even more complex with nested objects. So this is an example that we'll see over the course of the next few videos, where we have a disasters array, and then in this disasters array we have a number of different events. In this particular one, there is only a single event for the Nepal earthquake that has an event name, a date, a number of casualties, what the magnitude of the earthquake was, and the affected areas. And you could imagine that different disasters would have different keys. Like this one, as an earthquake, has a magnitude, but a terrorist attack wouldn't have a magnitude, or a hurricane wouldn't have a magnitude. A hurricane instead may have a category, or a tornado may have Fujita scale value. And we can read this in, and then we can access various elements within the nested object. But you'll notice that when you read this complicated or deeply nested JSON string in using loadS, loadS in the JSON package actually reads every field or every subfield of all this JSON and converts it to a dictionary or string or number as you'd expect. So here we see casualties and magnitude are not strings but numbers, as is population. So we can access this nested object. We see the Nepal earthquake and we have a date. We can add casualties field, if I can spell correctly, casualties. So we see we have a casualties field that gives us back some number rather than a string. And even if we call type on this, we'll see it gives us actually a number as well. And then we can iterate through the affected areas list that we had, so country, and we get Nepal, India, China, and Bangladesh were all affected. So that's going from JSON strings to Python dictionaries. We can go backward from Python dictionaries to JSON strings just as easily. So say we have some object that we create with Nepal earthquake, date, casualties, and magnitude. We can print this dictionary out just like we have before, but then we can call dump_s or json.dump_s on this object, which will take a Python object that's serializable or hashable and return a string that is a JSON version of this object. So you can dump this into a straight JSON string. You can add an indentation to this function by setting the named argument indent to some value, and we'll get a much prettier printed version of JSON as well, but it takes up a little bit extra space if you were saving this to a file. So here we see the Python object that has Nepal earthquake, a date, and a casualty. We have the associated JSON, which looks very similar to this printed out object form, and we have some more readable JSON with the 4 spaces of indentation after every value. Okay, so that's some very simple examples. And now we can graduate on to looking at Twitter in terms of its JSON. So I have an associated file called singletweet.json that has one tweet from Ferguson, Missouri back in 2014. And what we'll do is we'll open this file for reading and read the entire contents of this file into tweet file content. We'll go ahead and close the file, and then we can print out what this content contains. So if you run this, opening the JSON file, we have the raw JSON for this file. So here's all this content, all the metadata around this tweet. And then we can call load_s of the JSON package on this file content, and we get an object back. So we see these two things look very similar. We have contributors none, truncated false, contributors none, truncated false, with a little bit of change. Here we have false with a capital S, false with a lowercase f. These are slight differences in Python and JSON code. But now, rather than having to search through or do some sort of find and indexing within this string, we have a Python object with a bunch of keys that we can access. So these are some of the keys that you may expect to see in your standard tweet. You have a user, a created date, when it was posted, an ID, a stringed version of the ID, what the tweet's text was, where it came from, has it been retweeted, what's the retweet count, a bunch of information about whether it was in reply to anyone, and you can print out all this information. So we have the tweet text, we have this tweet dictionary with the key text, the tweet dictionary with the key user, but since user is nested, so we can actually see that. So here, user is a nested object within this JSON string. And one of the objects within it is a screen name field, which will give us the actual Twitter screen name for this person, versus the author's actual name, source, retweets, and some other things. So we can go ahead and run this, and we'll see what these examples are. So tweet text, Huffington Post reporter in Ferguson. This is actually, I guess, from Breitbart News and J. Andrews Biblo. We can see it's posted from Twitter for websites, which is some interface directly to Twitter. Now, at the time, this had not been retweeted or favorited, but that makes sense because most of the tweet content that we'll get is from the streaming API, which we'll talk about in a future video. The JSON is sent to you right as the tweet's created, so it hasn't had time to be retweeted or favorited yet. The tweet has no associated location or GPS coordinates, but it does have a guessed language that Twitter provides us that says it's English. Now we can go through another piece of this tweet called the entities field that gives us information about hashtags, user mentions, URLs, and media that are posted within this tweet. And we see there are no symbols listed, but there are user mentions. There are no hashtags, but there are URLs. And this lets us look at specific parts of the tweet that may be of interest. So the screen name Breitbart News was mentioned, and this tells us where in the string it was mentioned, who the user's actual name is, and that ID of that associated screen name. And we have URL, the URL that's shown, this very short t.co, which we see here, and then the expanded URL that goes to Breitbart.com. So I encourage you to play around with this to look and see what other entities and content are available to you within a tweet. But now what we'll do is talk about tokenizing tweets. So here we have the tweet text. This is a string, just like we saw in the previous video with State of the Union addresses. Tweet text is a string of words, but what we want to be able to do is tokenize those strings into distinct or discrete tokens that are words. So for this, rather than use the word tokenize function, NLTK actually has one that's specific to Twitter or these sort of microblog short text kinds of data sets. So you would expect the content of a speech from a politician that's spoken at some event to have a very different kind of format than a tweet, both in the fact that tweets have hashtags and URLs and emojis, and speeches do not, and the difference in usage of punctuation and such that we have to take into account here. So NLTK is nice enough to give us a tokenizer that's specific to this kind of data. So we can go ahead and print that out, and we see this twink tokenizer function. We go ahead and instantiate that, and it has a tokenize function within it where we can give it tweet text, and it will give us all the different words and punctuation within this tweet. And you may think that punctuation is worth filtering, and maybe we will, but emoticons are made up of punctuation, so you need to make decisions about whether you want to keep it or not. All right, so that's tokenizing a single tweet. Let's look at reading a number of tweets. So in the same place where you should get the single tweet.json file, I'll also provide a Ferguson_sample.json.gz file that has a selection of tweets from Ferguson and Missouri during the protests there in 2014. We'll look at that particular file. I kept it in the datasets directory above this. You may need to change this path, which I guess I should have said about this, because you may place it in someplace else. I think the easiest thing would probably be to place this file in the same directory as your notebook. So this tells us where this file is. We will have a list of tweets that we'll store. Right now it's empty. And then we'll call gzip.open. Now, it's important that you note the .gz file at the end of this Ferguson sample.json file. Because what this says is it's not just a JSON file, it's a compressed JSON file, kind of like a zip file. But the nice thing about JSON is since it's straight plain text, it compresses very well, generally at a ratio of about 10:1. So a file that is 100 megabytes of straight JSON might compress down to about 10 megabytes, which is very nice for archiving purposes. So rather than the standard open function that Python provides, we'll use the gzip.open function on tweet file path, which is wherever you should point to wherever you have this Ferguson sample file. And then for each line in this JSON file, we'll decode it into UTF-8 because that's the format that Twitter provides. And then we'll call load_s on this string. Now, Python's JSON package has a function called JSON.load that can load directly from a full file, but that assumes the file is one monolithic JSON object. And it's important to note that these JSON strings are not like that. Each line is a standalone JSON object. So when you call JSON.load S on each individual line, that will work. But if you call it JSON.load on the whole file, that will not work. So you can look through this notebook for more examples of this or for a better discussion of this. But what we'll do here is for each tweet in this tweet file path file, we will decode to UTF-8, parse the JSON out, and create a tweet object or a tweet dictionary from this JSON string and append it to our list of tweets. So we go ahead and run this. It'll take a moment, and once that's done loading, then we can call tweet count and we can call this line that will print out tweet count and then call length on this list of tweets. And we see we have about 132,000 tweets that were in this file. So now we can do some simple analysis on this. I encourage you to pay attention here because this is an example that you'll want to look at for your homework and that we'll rely on for the rest of the course. So what we want to do is pull out all these hashtags that are in these tweets. So this list comprehension may look complicated, but let me break it down for you. So first, we have for tweet and tweet list. That's the thing you want to look at first. This says for every tweet in our list of tweets, we have this tweet here. And in that tweet, we have an entities field, and we have a hashtags field within that. So all tweets have an entities field and a hashtags field. The hashtags field may not contain anything, but it should be there. So we'll say for every hashtag in this entities hashtag subfield, we'll look at the text of that hashtag, and then we'll convert it to lowercase just to account for any differences in capitalization that people have used. So what this will give us, this hashtag list, will have all the hashtags that were used in these 132,000 tweets. So you go ahead and run that. And then we can look at how many hashtags were used, which is just length of hashtags. And then we can call set on the hashtags, which will give us all the unique hashtags. And then we can count those up as well. So we'll see there are about 143,000 hashtags. So it looks like on average, tweets are using about 1.1 hashtags per tweet, but there are only about 8,000 hashtags that are unique in all of these tweets. So now we can take this hashtag list that we just created, #htags, and call NLTK's frequency distribution class on it. And this gives us the frequency distribution for hashtags, and we can call most common to get the 20 most common hashtags. And we see Ferguson, Mike Brown, Michael Brown, Justice for Mike Brown, and top conservatives on Twitter are the top 5 hashtags used in this data set. So we can do the same kind of thing here for most active users. So we don't have to quite do the same kind of list comprehension we did for hashtags, since every tweet only has a single user. So we have for each tweet in tweet list, we'll look at the user field and the screen name field within that user sub-object, and we'll call lower just to account for any potential issues in capitalization. This gives us a list of all the authors. So we can print out how many tweets there were. We can print out how many authors we've seen. So these two numbers should be the same. But then we can print out the unique number of authors by looking at the size of the set of authors, which will probably be smaller than the total author count. It cannot be bigger. And we'll use the frequency distribution again to find the 20 most common authors. So here we have Kive Ozone, Prince 1110 or 11110, War on Ferguson, Carolyn's Buddy, Missouri Sentinel as the top 5 users here. You see most users are only tweeting maybe 40 to 50 tweets in this time frame. All right, well that's it for an overview on using JSON and Python's JSON package to parse out social media data. So I encourage you to, as I said, to play around for this so you can explore the homework. Homework for this module asks you, as I said, to read in the tweets from the JSON file from Ferguson that I just showed you, and then find the most common authors. So you should be able to use the code from Module 3 here just to test it out, and find the most common hashtags. So both of these tasks you can pull from Module 3. Then I want you to find the most common mentions. So if you look at the content within entities, just like you did with hashtags, you should find a user mentions field that you can find here. And then I want you to find the most common tokens. We've already looked at finding the top 10 tokens in Module 2. I want you to do the same kind of thing here with the Twitter data from Ferguson. But keep in mind, I want you to remove stop words using the NLTK stop words corpus, just like you've seen before. And that's it. I also am offering extra credit for this. If you want to do something a little bit more complicated, you can find the top 5 retweets in this data set. All right. Well, that's it with Module 3.